Okay. Hello, everyone. My name is David Kennett, and I am here today with my teammates Henry, Tregery, and Yuting. Today, we are going to review data based on Southwest Airlines. Our project focuses on predicting and reducing flight delays, which is one of the most operationally complex challenges in the United States airline industry. Let's get started. So here's a quick roadmap of what we're going to cover today. We'll start with some of the background on Southwest Airlines, and then we'll walk through the business problem driving our analysis. From there, we'll cover how we sourced and prepared our data, followed by a deep dive into each of our three models, which are logistic regression, random forest, and the gradient boosting model. Then we'll compare our performance, their performance, address the ethical concerns of our work, and walk through a few key graphs, and then we'll close with some of our conclusions and recommendations. Southwest Airlines is the largest domestic low-cost carrier in the United States, operating a point-to-point network that serves over 100 destinations. Unlike hub and spoke carriers, Southwest model means that delays have a cascading effect across the entire network, as is a single disruption can cause a ripple through dozens of subsequent flights. With roughly 4,000 daily flights, 60,000 employees, and about 130 million passengers served annually, even small improvements on-time performance translates to a significant financial and reputational gain. On-time performance isn't just a metric for Southwest, it's central to their brand identity. And I will hand it off to Henry.
So what is the actual cost of a flight delay? In our data set, the mean arrival delay for delayed flights was about 62 minutes, with a maximum recorded delay of over 1,000 minutes. Operationally, delays disrupt rotations, crew scheduling, and passenger connections, all of which trigger additional costs. The US DOT reports that delays affect tens of millions of passengers every year, and the financial toll includes extra fuel burn, crew overtime, and passenger rebooking expenses. Most notably, Southwest's 2022 holiday meltdown cost the company approximately $800 million dollars and caused severe damage in customer trust. This is exactly what the kind of event predictive modeling is designed to help prevent. Our data from Kaggle dataset is based on US DOT flight records. We filtered it down to Southwest airline flights only, using the carrier code WN. Can you go to the next slide? Removed and canceled, removed using carrier code WN, we removed, canceled, and diverted flights and sampled up to 200,000 records. A key priority in our prep work was preventing data leakage, so we dropped any post-flight columns that wouldn't be available before departure. We then engineered our binary target variable, is delayed, defined as any arrival delay greater than 15 minutes, consistent with the DOT standard. We also extracted departure and arrival hour from the scheduled data and bucketed any airport outside the top 25 as other to manage dimensionality. Finally, we one-hot encoded our categorical variables, applied standard scalar to our numerical features, and used an 80-20 stratified train test split with five-fold cross-validation to ensure our results were robust. Next slide, please. Moving into some model analysis. Our first model was logistic regression, which serves our linear baseline. It uses sigmoid function to estimate the probability that a given flight will be delayed, then converts that probability into a binary prediction. We applied L2 regularization with a C-value of 0.1 and used the liblinear solver, along with the balanced class weights to address the imbalance in our dataset. The model achieved a test ROC AUC of 0.698 and an F1 score of 0.404 for the delayed class. Its recall on delayed flights was reasonably strong at 0.671, meaning it correctly flagged about two-thirds of actual delays. However, precision came in at only 0.289, so there is a meaningful false positive rate. The main value of this model is its interpretability and its role as a performance floor for comparison.
Our second model was a random forest with 200 decision trees. Rather than relying on a single tree, random forests build many trees on random subset of the data and takes a majority vote for the final prediction. We constrain tree depth to 10 and set minimum samples for split and leaves to avoid overfitting. This model improves on logistic regression across the board, achieving a test ROC-AUC of 0.7129 and matching F1 of 0.4051. Most notably, it produced the highest recall of the three models at 0.726, meaning it caught nearly three-quarters of all actual delays. The trade-off is that precision remained low at 0.281, which means the model generates a fair number of false alarms. Still, in an operational context where missing a delay is more costly than over-alerting, high recall is valuable. Our third and best performing model was XGBoost, a gradient boosting algorithm that built trees sequentially, with each new tree correcting the errors of the previous one. We used 300 estimators with a learning rate of 0.05 and a max depth of 5, along with L1 and L2 regularization to control overfitting. XGBoost achieved a test ROC-AUC of 0.7461, the highest of all three models, and an F1 score of 0.4347, also the best. It maintains strong recall at 0.705 while improving precision to 0.314. The combination of strong discriminatory power and better balance between precision and recall make XGBoost our top candidate for further development. If we were to move toward production, this is the model we tune and validate first. As a summary, this chart looks at the performance of all three models side by side. You can clearly see the progression, logistic regression at an AUC of 0.698, random forest at 0.713, and XGBoost leading at 7.746. The F1 score tell a similar story, with XGBoost 0.4435 standing above the other two. One takeaway here is that while all three models operate in a similar range, XGBoost's consistent edge across both metrics make a compelling case for its use as the production model. There's also room to grow a UC score in the mid to high 0.70s, suggests meaningful predictive signal, but incorporating richer pre-departure features like weather data or ASOS report could push performance further.
Before we move on to conclusions, we want to address the ethical dimensions of this work, because deploying a predictive model in a real-world setting carries responsibilities beyond accuracy metrics. First, flights contain sensitive behavioral data, so passengers must provide informed consent regarding how their information is used. Second, models trained on historical data can inherit systemic biases. Certain routes or airports may be disproportionately flagged, which warrants regular auditing. Third, we want to be transparent about our models' limitations. Strong test set performance doesn't guarantee reliability in production. Fourth, any delay predictions used to drive rebooking or dynamic pricing must be applied equitably. Passengers on high-risk routes shouldn't be financially penalized. And finally, the scheduling data powering these models must be secured against misuse or market manipulation.
Moving into some of the key charts, this histogram shows the distribution of our target variable, which is delayed, across the dataset. About 81.7% of flights in our sample were on time, while only 18.3% were delayed. This class imbalance is important. A naive model that simply predicted not delayed for every flight would achieve over 80% accuracy while being completely useless. That's exactly why we applied balanced class weights in all three models, so the algorithm paid proportional attention to the minority delayed class rather than optimizing purely for overall accuracy. I think
This
Henry.
graph, yeah,
Okay.
this graph breaks down average delay rates by day of week. Day 4, Thursday, shows the highest average delay rate at around 0.200, followed closely by Friday. Saturday notably has the lowest delay rate at approximately 0.155. This pattern makes intuitive sense. Mid to late week sees peak business travel demand, which strains aircraft and crew rotations. Saturday likely benefits from lower overall flight volume. Day of week turned out to be one of our engineered features, and this chart confirms that it carries meaningful predictive signals.
This graph shows average delay rates by origin airports for Southwest's top 5 busiest departure hubs. BWI, Baltimore Washington International, has the highest delay rate at roughly 0.23, followed closely by MDW and LAS. Airports bucketed as other show the lowest delay rate at around 0.15, which makes sense since those smaller markets face less congestion and fewer cascading delay effects. This reinforces Origin Airport as a meaningful feature in our models, and operationally, it suggests that Southwest might prioritize buffer time or proactive staffing at its highest risk departure hubs. To wrap up, XGBoost is our strongest model, achieving the best AUC and F1 scores across our test set. All three models demonstrated solid recall, but faced the shared challenge in precision, meaning false positives remain an issue that threshold tuning and additional features engineering could address. We handle class and balance consistently across all models using balanced class weights, and our results suggest meaningful predictive power even with pre-flight features alone. Looking ahead, we recommend deploying XGBoost with real-time pre-departure data, conducting hyperparameter tuning via grid search, and building a model monitoring pipeline to detect drift over time as flight patterns evolve. Thank you for all of your time. And